Today I'm going to be showing you how to balance really complicated equations really simply. So the first one we have is the reaction of potassium nitrate and sucrose, also known as table sugar, which leads to the formation of potassium carbonate, carbon dioxide, nitrogen gas, and water vapor. There is a cheat code for this, which actually works for pretty much every chemical reaction. What you need to do is find out the deficit of one element in one of the compounds and the surplus of one element in another. So this sucrose is a carbohydrate, so you can just remove the hydrogen and oxygen in the form of water, and the remaining carbon needs 24 oxygen to fully oxidize it. Whereas the potassium nitrate, 2 of those potassium nitrate will give 5 oxygen, because potassium nitrate is a combination of potassium oxide and nitrogen pentoxide. In order for that to convert down to nitrogen gas, it has to release 5 oxygen. So basically what we do is we have 2 on the potassium nitrate and 1 on the sucrose, but then we multiply the potassium nitrate by 24 and the sucrose by 5. So we know that we need 55 water, and since there's 48 potassium nitrate, we need 24 N2, and since there is 48 potassium nitrate, we also need 24 potassium carbonate. And now we can fill in the rest of the things. The sucrose is obviously 5, like we discussed later. The carbon dioxide is 36 because that's how many carbon are left over. And the water is 55, like we discussed earlier. Now we have an easier one. It's the reaction of copper 1 sulfide and nitric acid. So copper 1 sulfide is pretty low oxidation state, so it will readily be oxidized to the 2+ oxidation state and leave behind just some copper. So you have CuS and copper. So the copper sulfide, to become sulfate, needs 4 oxygen, which can be supplied by 8 nitric acid molecules. And the copper, to turn into copper nitrate, needs to react with 4 nitric acid to give copper nitrate, NO2, and water. So basically what we can do is we can just sort of add the equations up, and it's pretty easy after that. And now we have one you might be kind of familiar with. Diazenonyl tetrapolyhexafluoroantimonate. Sorry about that, it's a pretty long name. So as you can see, the xenon has left, which means that there is a surplus of 1 fluorine on the, I'm not even going to say its name because it's too long. So that means we have to multiply it by 4, because when fluorine reacts with water, you need 4 fluorine atoms or 2 fluorine molecules. And now that the xenon and extra fluorine have left, we're left with 16 antimony pentafluorides, which each need 4 water to hydrolyze fully. So we need 64 extra water. And don't forget, the extra fluorine needs 2 water to react with, because it will make 4 hydrogen fluoride and 1 oxygen molecule. And now everything else is really easy. You can easily figure out the antimonic acid, because there's 16 antimony, and the xenon because there's 8 xenon, and the hydrogen fluoride because there's 84 fluorine. And then we have this one, which is an absolute beast. So I'm going to simplify it for you. So the pyridinium chlorochromate, in order to form these products, requires 29 fluorine atoms. And this, I'm not going to say its name because it's too long, molecule gives 9. Because the antimony pentafluoride will decay releasing fluorine, which is why it's an oxidizer. So So we put 29 on this side and 1 on the pyridium chlorochromate and 9 on the pyridium chlorochromate side because you have to switch them around. And then you multiply it by 2 because otherwise you would get a half of a molecule, which is not a thing. And after that, it's just a matter of multiplication. Simple as that.